Hello, this video is going to be a little bit different. I recently gave a lecture at a compiler's course at the University of Michigan, a guest lecture, and this is going to be the recording of it. There's going to be some light editing because, yeah, the recording quality is a little bit low, so there will be parts where I have to dub over or change the actual video feed. But it turns out that the university lecture recording equipment leaves some quality to be desired. So if I ever do this again, I'll do a local recording and probably have a little bit better quality. But anyway, let's jump into it.
We'll have lots of time at the end because I don't think my actual presentation is going to last that long, but that's fine. So my name is Anthony. I'm also known as Anthony Writes Code, or Acetilly, or Anthony or various other monikers on the internet. I make YouTube content sometimes. I also stream on Twitch. Usually I work on open source software, and I sort of just turn on the camera and start talking and working. And I've built a community over time, and I really enjoy doing it. My YouTube channel is mostly me answering questions that get asked a lot in chat, mostly as a way so I don't have to keep repeating myself over and over. But I found that I've sort of built a wealth of knowledge over time, and often I refer to my own content when either mentoring junior engineers or trying to figure out how something actually works. I'll ask me, how did this work? A little bit of background on myself. I was a student at the University of Michigan. I graduated in 2013 with a computer science LS&A degree and 4 credits short of a biochemistry degree, which is a fun story, but probably not for today. I've worked at a bunch of different tech companies, as my introductions led on to. The first was Yelp, where I actually started as a front-end engineer, writing CSS, JavaScript, and HTML, twiddling pixels for product managers. I found that it was really hard for me to get my job done as a front-end developer because I was constantly waiting on back-end engineers to get my job done. And so what's a great solution to that? Become a back-end engineer. And then I found as a back-end engineer, it was also really hard for me to get my job done because I was waiting on tools, infrastructure, developer environments, CI, testing, validation, deployments. And so I figured, I bet I could work on those things. And that's where I found the stuff that I really like working on. I really enjoy building productivity tools and making people more effective. And so that's where I kind of found my stride. After being at Yelp for 5 years, which is way too long to be at a single company, I left to take some time off. I worked on some open source stuff for about 6 months-ish, dicked around in Toronto and had a fun time there. And then I worked at Lyft. I was there for 2.5 years. I was hired onto a team that was supposed to be responsible for the entire production execution of Lyft and the entire development production of Lyft. Obviously, this was the part that I enjoyed more. But it was 4 of us responsible for a couple hundred engineers and running the entire site, which is terrifying. Eventually, that team split into 2. I took on the developer productivity space and built that up over time. Mentored many engineers, built a team, and really enjoyed working on that. Then the pandemic happened, and Lyft wasn't so useful during the pandemic, and all of the sales numbers were down, and so they had a large layoff, and 20% of the company was just gone. I was part of that 20%, and actually during that time, maybe we jump ahead a little bit, sure. During that time, I actually built a startup that is profitable somehow. So it's great to take 9 months off of the corporate grind and build something that I wanted to build for myself, that I didn't really care if it was profitable, but I wanted to build something that I enjoyed, and then it turns out other people were solving the exact same problems that I was, and so I could sell it to them. After that, I worked at Stripe. I was hired to build a Python infrastructure team. Stripe has a bunch of different programming language teams. Ruby, well, now they only have Ruby and Java, but that's part of why I left. For 9 months, I worked on building a Python infrastructure team, and the leadership decided that they were going to pivot everything to Java development. Yes, in 2021, Java was apparently the language they were choosing. Despite 80% of their code being written in Ruby, they got rid of all of their language teams and said, let's build Java. I think my favorite part about this story, though, is the framework They called it Horizon, aka we will never achieve this. But anyway, I wasn't too plussed about that, and so I started looking for a new job. Around that time, I was reached out to by the co-founder of Sentry, who wanted to build a developer productivity team, and it turns out I am the person to do that. And so I worked at Sentry for 3.5 years and built a developer productivity team. Recently I left Sentry, and I'm kind of doing nothing right now, which is actually amazing. I'm really enjoying it. I say I'm doing nothing, but really I'm maintaining my startup. I'm working on a bunch of open source stuff. I'm still doing YouTube and Twitch. I am also working with Lingzha and Jason on Joseki, which is a programming language, and I'm still doing all sorts of open source stuff, which I want to talk about as well, even though it's already sort of been spoiled on some of the stuff that I do in open source. I maintain a bunch of things, too many of them, I would say, and it takes a lot of time. An honest reflection is I wish I did less open source a few years ago, such that I would maintain less now, but we're here and I can't really change that, so in a lot of ways, I'll just enjoy it. Some cool things that you've definitely used, if you've ever run Docker, Python, Go, Ruby, yeah, I mean that's a few of them. If you've ever run those core pieces of technology, in some way you've run code that I've written, which I think is cool in some ways. I actually, complete tangent, changed the type system of Go forever on accident, and yeah, that was not my intention, but I was just trying to make a stupid thing work in Python, and something pointers. Anyway, some of the stuff that I created or maintain, I created Precommit. It's a GitHooks and linter and code formatter framework. It is probably the cornerstone to developer productivity and kind of the basis that I do most of my work and try and center most of my work around. I created this tool during college as a way to force my groupmate partners to give a shit about code style. I don't know that it was super successful, but I found once I was in industry that it turns out everyone has this problem and no one solved it in a great way. A lot of people are writing 2,000-line bash scripts to solve the same thing. Why not make a framework that makes this really easy for everyone to use? So I made this thing. I'm also the maintainer of Flake 8, which is a linter tool in Python. I do a lot of, again, code quality, linters, code formatters, testing, automation. That's the kind of stuff that I really enjoy and the bread and butter of what I build in open source. I'm also a core dev on PyTest. Well, legacy core dev because I've been less active recently, but I have the commit bit, so it counts. And I made my own text editor among 70 other projects, which you'll see throughout this, but it is a fully featured terrible text editor with syntax highlighting. You might also wonder why I'm using light mode. This is a tip that they never teach you when presenting. You should always present in light mode so that on a screen, you can see it in the back. Yeah, so please, if you're ever going to present, use light mode. I don't actually use light mode when streaming though, so do as I say, not as I do. But yeah, I wrote my own text editor from scratch. I would not recommend doing it, but it was a fun experience, and I learned a lot about how terminals work. And for 2 years, I worked without syntax highlighting, so until I built the syntax highlighting engine. Yeah, I talked about my profitable startup. It's based around the open source framework that I talked about before. Okay, I've just talked about code stuff. Let's be a little more personal here. This will be kind of the director's cut of my not Hinge profile. This is going to be more personal things. I like to cook and bake. This is my interpretation of Cosmo's Bibimbap. That was really good. I'm going to make that when I get home. I like shitty pop punk music. This is me in Vegas at a festival that got canceled because it was too windy, but I often go to pop punk concerts with my mom. This is not my mom, by the way, in case it wasn't clear. I like to drive fast cars. I really like spreadsheets. These are my two favorite spreadsheets. This is my shiny Pokemon spreadsheet. I've caught every shiny Pokemon that's possible, including every gender and form. That's too much of my life, but I also... This is my running spreadsheet. It's also my bike machine spreadsheet because I've basically cataloged all of my, you can see when I didn't want to go outside in the year 2020 and stopped running after running a marathon. But yeah, I like spreadsheets. I'm also into running. This is me running the Ann Arbor Marathon, my marathon 1 of 2 from a couple weeks ago. This is the only pleasant photo from this entire race because running a marathon is miserable, and this is in the first 30 seconds, so this is before everything is in pain. I also like biking, especially without handlebars, as we can see in this photo where I'm going 17 kilometers an hour and for some reason taking a photo. Don't know about that. I also enjoy rock climbing. I go several times a week. I'm not very good, but it's fun. I also like electronics and soldering. This is a 3DS that's been taken apart and had tiny wires soldered to test points. Those are each about 0.5 millimeter wide, and so I got really good at fine soldering, and it turns out the device still works. This is a project to automate button presses and touchscreen inputs on a 3DS and be able to control them with computer vision. So yeah, that's a little bit about me. What I'm going to be presenting today is basically this YouTube video, but with a lot of other tidbits mixed in. Why am I presenting this and why am I here at all is actually kind of a fun story. When I was in school, I never got to take compilers as a course. It was one of the few that I wish I would have had, if I could go back in time, like, take compilers. It's going to save you so much time. You're going to write so many terrible parsers over the years. Please take this course. So I hope I can actually take this course at some point. But the summary of this video is basically I'm going to show you some weird shit about Python and then be able to explain it using the various levels of how the parser and compiler in Python work, and then how that compiled code is executed at runtime. This original video is only 11 minutes, but we got some other cool tidbits that have built up over the year. This is also pandemic era me, so it's my apartment in San Mateo with a really shitty webcam. But anyway, without further ado, I guess we'll jump into things. I'll be using this visualization tool that I wrote this weekend on stream to show some stuff later, but for now it's not going to do anything. And that's kind of okay. All right, so Python. When people usually think of Python as a programming language, they think of it as interpreted, slow, a scripting language. But I was surprised when I first learned Python to learn that it's actually compiled. When you run Python, it parses the input, it turns it into a token stream, it turns that token stream into an abstract syntax tree, and then it compiles it into a bytecode. And then there's a virtual machine that runs that bytecode as it executes. And we're going to take a look at each of those parts of the pipeline. I spend lots of time looking at the tokenization in AST for writing linters and code formatters. A code formatter, taking a token stream, manipulating it, and then writing new code out. And an AST is really helpful for figuring out how the code actually looks. And so you can say like, oh, that's an unused variable by analyzing the reads and stores to a variable. And things like that. This is my outline. So, all right, tokenization I think is the first step that I think about when thinking about compilation. Of course, let's just show the final product and then we'll work backwards as well. So if you have a Python file, I'm just using my text editor. Let's just make a very simple function called add1. We're going to take it a parameter. This is going to be non-idiomatic code sort of intentionally so that we can show off some stuff later. Like you would probably not assign a variable named 1 and then do return x plus 1. You would probably not ever write this function, but trust, it'll make sense later. And I guess let's call it add1. And just to show that it works, of course, we get 6, and that's cool. You may have noticed if you've written Python, I realize that Umish is C++ or bust for the most part, but unfortunately, I've been stuck in Python for a decade plus now, so that's what we're going to be talking about. You may notice if you ever run Python scripts that you'll end up with these PyCache directories. Or when I originally gave this video, this YouTube video, Python 2 is still popular, and so you would see .pyc files. But no more Python 2, thank goodness. Oh wait, there's still a pyc file. It's just hidden in this directory. And this is actually the compiled output of Python. And kind of interestingly, you can actually run the compiled output of Python directly. So if I were to delete the Python file, you could still run this. We'll be diving deep into the contents of this file in a bit, but let's start with the tokenization. So I think that's probably the first step of I don't know, I didn't take a compiler's course, so I don't actually know this stuff. This is just my intuition over time. The first step should be tokenization, surely. Python has a module built in called Tokenize, which implements the tokenization. That's not entirely true. Well, in the version of Python that I'm running, there's actually two tokenizers, one that's actually used and one that's this module, but it does mostly the same thing, so we'll just pretend. And the tokenization takes the source code and turns it into a series of tokens. These tokens are then interpreted by a grammar, and then that grammar is then turned into an AST, and then the AST is turned into machine code. In this particular case, you can see that there's actually this fake token at the beginning of the file. Yeah, that's not the first token. OK, the first token was def, though. This is what's used to define the source encoding. Almost all Python files are UTF-8 nowadays, so this can mostly be ignored. But you can see here the syntax positions, the token name, and well, the token name is name in this case, but and each token in this file. One kind of downside to the Python tokenization is most of the white space actually isn't shown here. So you can see, for instance, between x plus 1, the original source had white space there, but the Python tokenization leaves it out. This is because the actual interpreter doesn't care about most white space in a file. Some of it is important, as you can see from this indentation here, but most of the rest of white space in Python actually doesn't do anything. There are actually two types of new lines as well. That's another neat thing to point out. The NL is the useless new line. This one, for some reason, is in the tokenization, although it is also ignored. And this is the syntactically important new line. Just some small things to point out here. OK, I promised you I would show you some weird shit about Python, so I'm going to show you the first weird thing. OK, in Python, there are a bunch of different ways to make strings. For instance, you can have single-coded strings, you can have double-coded strings, you can have raw strings, F strings, T strings, you used to be able to have U strings. You can have triple-coded strings, which is fun too. But they basically all function the same way. They have no significant meaning between the two. What if I told you you could have a half triple-coded string? Does this look like it should be correct syntax? Oh wait, hold on. Make it double code on both sides. Has to be the same code type. This shouldn't be correct syntax, right? This looks like nonsense. It's not a triple coded string. However, it also works. But if I do it the other way around, it does not work. It's asking for more input, and obviously I don't have any more input. Unterminated triple quoted string literal. So how does this work? Fortunately, our tokenization module can actually help us understand why that's valid syntax. Spoilers, this is actually the same as this, and the same as this. There's implicit concatenation of string literals, similar to C, and I think C++ has the same thing. Well, it should be inherited, but. Also, if I type nano on the terminal, it's actually an alias. I used nano for years, and it's sort of inspired my text editor. And actually on a keyboard, if you type nano but move your hand over, it becomes Babby, which is my text editor. So I still haven't broken the brain. Well, I've broken the brain, but I haven't fixed the association with typing it on the terminal. So if you see me type nano, that's why. Let's make a new file. So let's put that triple-coded string here, or that partially triple-coded string here. We'll do it with single quotes this time. Why not? And if we run the tokenize on this, tokenizer, you can see here that we're actually getting two separate string tokens. So this is kind of a hint to why Python is doing this little weirdness here. It just looks like a half triple-coded string, but it's actually two string tokens. They're actually joined together, and that's the first weird thing I'm going to show you today. I actually wrote my own version wrapping the tokenizer.
So
Yeah.
why didn't it work the other way around?
So the reason it didn't work the other way around has to do with how the grammar parses this. When it sees this token here, this triple double quote, it says, oh, I must be looking for another triple double quote. Whereas in the other case, well, Python used to be LL1, which I don't know what that means, but surely someone here knows what that means. It's now a peg parser, so it could actually support this, but it doesn't. They were probably like, this is nonsense, we shouldn't make this work anyway. But in this particular case here in LL1, it recognizes this, I guess they're not really, it's not a separate token here, but it sees the double quote and says, oh, I must parse until I see the other double quote. Because the actual original tokenizer cheats a little bit. But anyway, it doesn't backtrack, and so it couldn't figure out the reversed one. And that's probably a good thing, because the syntax error if you were able to write this, the source would be way worse to read. The fact that this exists is kind of just a silly thing. But yeah, I was saying I actually wrote a tool that wraps the tokenizer because I found that the output that it currently has is not very useful for writing code formatters because code formatters do care about white space, whereas the interpreter does not. And so oops, that's not how you spell it. I made a tool called Tokenize-rt, which RT standing for round trip. So if we look at that original file here, you can see that I've actually included a separate token for unimportant white space, aka white space that the interpreter doesn't care about, but is important for doing code rewriting here. So you can see there's a bunch more tokens here. But anyway, one of the many tools I've written over time to help make these things easier to work on. Also, you'll see that the UTF-8 token isn't there because it's not useful. So I just left it out. This tool also adds some other stuff. So for instance, do I even bother showing this? Sure, why not? In Python, you can have escaped new lines, and this is actually just one line to the interpreter. And if we ask the tokenize module about it, yeah, you can see that backslash isn't there at all. And so it doesn't really show that in the source. But obviously that is also important for code formatters. So I have, again, another fake token here. Fun fact about this backslash here. Is this how you do it? I don't even remember. I have to make a Python file that doesn't end in a new line but ends in a backslash. And I seem to remember, if you look in an old version of Python, it'll run it. Yeah, okay. So this syntax error is actually something that I contributed to Python. Because it turns out that, you shouldn't be able to escape nothing at the end of your file. So anyway, this is some weird edge case that someone brought up in a GitHub issue once. And so changed Python for the better here. Okay, so that's tokenization.
Can I have a question?
Of course, yes. And if anyone who wants to interrupt with questions, please do. I stream on Twitch, and it's just constant interruption here, so I'm completely okay with that.
So Python actually hand-coded the tokenizer, right? They didn't use any tools or whatever. So they decided to just start from scratch and,
Yes and no. So the original version of Python, yes, they wrote their own tokenizer from scratch because it was 1991 and there weren't great tools for writing a full tokenization. I guess Yak existed back then, so why didn't they just use that? Maybe they did. Guido was probably like, "Fuck that! That's not very useful. We're gonna write our own." But yeah, so yes and no. Python did write their own tokenizer and did write their own parser generator, but they've also used other tokenizers and parser generators over the year. The current one is implemented from scratch, though. They wrote their own parser generator. They wrote their own conversion to C, and yeah, they're not using some off-the-shelf one, which. I don't know. I think it would be better if they used an off-the-shelf one, because then at least other people could understand how it works instead of Pablo and 4 other people. But yeah, that's how things go.
How was that more recent decision made? Because there's a PEP system. How many people know what PEPs are? Python Improvement and proposals?
Enhancement.
Enhancement proposals. I was like, that sounds like yeah. So is there a PEP for this, and what is a PEP? Since I asked.
Sure. So PEP, or Python Enhancement Proposal, is the way that the governing decision-making model happens in Python. Basically anyone, literally anyone. I could make one. I don't want to because it's a lot of work. Anyone could make an enhancement proposal to Python, go through the process of getting a core dev sponsor on it, and eventually having the steering console, which is how the current governance model works, vote on whether that enhancement should happen and then implement it to Python. Note here that I say Python, but really I'm referring to CPython because Python the language and CPython the implementation are. I'm being too pedantic and connected. There are other implementations of Python, and their governance models are completely separate. They usually follow the language decisions that are made by CPython and the Python Foundation, but they're separate. And your specific question about how did this not get figured out in a PEP? Python recently changed the grammar type. It used to be LL1. It is now a peg parser. We'll actually talk about this later because there's some nice little quirks there and some things that I really like about the peg parser, but also some things that I really dislike about changes to Python that were enabled by it. But the proposal to change the grammar from LL1 to peg outlined. Actually, I mean we can probably find it, right? See peg, parser, PEP. And the other thing that's really nice about this is all of the PEPs are publicly available. You can see all of the discussion that happens on them, except for the final voting by the steering council. That's done in a private meeting, which...
they should stream it. What are they doing?
They should, but there are things that they discuss in there that are not for public consumption. So I kind of get why they do it, but at the same time, I think the PEP decision process should be a little bit more transparent. But anyway, they wrote out a whole, I say they, it's Pablo again. Well, yeah, Pablo did almost all of the work on this. But they wrote out a proposal here. They talked about what I guess I could learn what an LL1 parser is by reading this, probably. And they outlined kind of their rationalization for why they wanted to improve the parser. If I remember correctly, most of the rationalization here was Python wasn't really LL1. It was parsed that way, and then a bunch of second or third passes to the output were converting it or discarding possible grammars. For instance, I want to say assignment in Python actually doesn't, or assignment expressions in Python doesn't actually fit in LL1 because you need to force a name token on the left-hand side. But the actual parsing of it could parse any atom in that space, and so there's a second pass where they discard that. And I think they talk about that in here specifically. Oh yeah, in fact, this is exactly the thing I remember. Named expressions don't really work in it. This is actually the thing that I was going to talk about later, which is the one thing that I really like about the new peg parser is there can be a comma after this R here. Trailing commas are a beautiful thing in programming. They preserve get blame. They make it so that your code looks the same if you reorder parts. And any place where you can't have a trailing comma is painful. It's actually a big part of why code formatters are really nice because they can enforce consistent style here and enforce that you will always preserve get blame. When I talk about get blame, if somebody were to add another one here, they would have to actually modify 2 lines, including one unrelated line to add the thing they want. But if there's a trailing comma there already, it's simply adding a single line or removing a single line, which is a great quality of trailing commas. But it turns out that this syntax construct is not at all representable in LL1 without ambiguities that weren't possible to resolve in the parser. And so that was one of the rationalizations for moving to a peg parser. The bigger rationalization was to implement new complicated syntax features that would have been ambiguous in the previous parser. Things like the match statement, assignment expressions, infinitely nested F strings, other stuff like that. Yeah, and so the PEP process, they outlined all of this, went through the proposal, I believe they actually had a functioning prototype by the time that it was decided on so that you could see what the actual effects were going to be in Python itself. And then yeah, it eventually got merged. This was actually a really slow rollout, a very carefully done one, and I think this is one of the good examples of code changes in Python where it's not something that's just a rug pull and good luck, you deal with the changes. This one was actually really well thought out. It was opt-out in the first version of Python that it landed in, which I believe was 3.9, and then once they were confident that it was stable, it became part of Python 3.10. But this is, I think, one of the better PEPs and one of the better times the process actually went well. Yeah, okay, cool. So we talked a bit about tokenization. Next, I want to consult my little, oh, yes.
Just a quick question on tokens. There are no tokens for tabs?
Yes and no. So if we take this, and it's actually really hard to turn off tabs to spaces in my editor intentionally. If we look at this, there is actually a tab. Tabs can be represented in the tokenization, but it'll be represented as this indent token. So prior to this, it was indent and then a 4-space string. This is indent with a tab. However, if you put tabs in, again, in like not useful syntax locations, like here, this is not a useful white space, they won't be represented at all in there. They're just left out. Of course, Tokenize-rt does this correctly. Well, I don't want to say correctly, but
But you mean correctly.
but I mean correctly. Yeah, and so it'll preserve, wait, where is it? Yeah, here. No? One of these. Somewhere in there, there's a tab. And it actually preserves the character rather than leaving it out. Oh, yeah, it is this one. Yeah, I got the right one. So yeah, tabs are part of the tokenization. Indentation in Python, when it is significant, is represented as a token. When it's not, it's left out. Cool. Okay, so from how I understand parsers and compilers, start with tokenization. Next, you go to an abstract syntax tree or a concrete syntax tree. The difference between concrete and abstract being that concrete is really nice because you can refer to syntax positions, whereas abstract, you usually don't have that information. Unfortunately, Python's syntax tree is a mix of the two. It is a abstract syntax tree with some amount of syntax positions that are often wrong. And when you write linters and code formatters, those subtle incorrect things are actually super annoying. I just thought of another cool demo of the AST that I will show in a sec that wasn't in my notes. So you're going to get a bonus piece of content that I didn't plan for. Python has, again, another module that you can run to show a parsed AST for a particular module. Actually, let's remove the tabs from this because we don't really want tabs. We want spaces. Okay. Oh, that's the wrong one. And so if you run the AST on, or the AST module on a Python file, you get a sort of representation of all of the syntax parts of that tree. You can see here that we have that function definition, we have the name of it, we have its body, which is a series of statements. There's an assignment statement, a return statement. We can see how a name is stored with this particular value. I actually think this output's super ugly, though. I find that the parentheses here are really hard to read. So, of course, I wrote my own version of this that sucks less. Well, and actually, I wrote this before the AST module did this. They did that. They did that later after seeing that people thought this tool was really cool. So they were like, well, we can just do that in Python. So I wrote a similar version of this, no show offsets, t.py. So this is, I mean, it looks basically the same, but I think this is a little bit more pleasant to read.
I didn't know you wrote AST pretty. I actually have used it.
Oh, yeah, I use this.
Pay attention to who created it. That's wild.
I use this thing all the time. But I also, and there is an option to the standard lib one to do this as well. It can also show the code offsets here. I intentionally hid them because they can get a little bit noisy. Yeah, the output's almost twice as long with them on, but anyway, this is sort of the AST representation of Python, which, yeah, kind of the step before it gets turned into a bytecode. Well, one of the steps before.
One quick question.
Yeah.
So there's this context store and context load, and what I understand about it is the lower levels of the interpreter has to know how to treat symbols in your program as to whether or not they're going to be written or writable, etc. in the context.
Yep.
That's something I haven't seen a lot of in other languages. Like, what is that? And why do we have it?
The CTX as well.
Yeah. So interestingly enough, this is actually an artifact of older versions of the AST parser in Python. From what I understand, from reading too much of the C code, that CTX actually doesn't do anything anymore.
Oh, thank God.
But it is accurate.
Yeah. It has to be. It breaks.
And the reason for this, actually, being able to explain this context is actually really useful. There used to be a third context, which I don't think is used anymore.
DL.
Oh, I guess there is the del context too. Yeah, I forgot about that one. But being able to see this is actually super useful. Actually, you know what? We'll use my module. Sure. If you do, for instance, x equals 1, false. Of course, yeah. So here it's very clearly in an assignment context. So we get this store here. This is saying that Python is treating this name as a writable field, as opposed to reading one. However, if you look at, for instance, let's say we did print 1 instead. Print is not a keyword in Python 3. It's just a normal function now. And so when it actually retrieves that name, it is going to be loading it from the environment and then calling it. There's actually a more complicated situation here where, I don't know, you'd have to import sys, but we're just looking at the AST, so this isn't going to be a valid program. But if you load an attribute, you also load the attribute of the attribute, and then, actually, where is it? Sys, yeah, so we have the name that's loaded here, we have the attribute that's also loaded here, and then the second attribute that's also loaded here. And so this helps it differentiate between loading and storing. This also means that if you assign to things, you have both a mix of loads and stores in the same statement. So for instance here, it has to load the sys name so that it can retrieve the standard out attribute that it's actually going to write to, and then it can assign to it. So you kind of have a difference between load and store there. Yeah, there used to be 4, I forgot about del, that's a good point there. But there used to be a 4th one that I don't know if it exists anymore. Yeah, so there's context equals del. I guess we can look at ast.del.bases. Yeah, and ast.expr_context. We can do a little reflection. Let's function right. Load, store, del, load, store, and param. Okay, param is the one that doesn't exist anymore. I think the others do though. Oh, pparam. Yeah, so this, nope. I think the store and load ones are also gone. And in fact, I think if I open up Python 3.14, ast.expr_context.subclasses. I know we're wasting time on this, but I'm curious. Oh no, they're still there. Okay, I think they're deprecated, but I don't think they do anything anymore. Yeah, okay, so AST. There was a funny example I wanted to show for this, but I forget what it was, so we're going to do this real quick. Oh, yes, okay. This one is evil. All right, so false is a Boolean in Python. It is just a normal object. It exists. There's also true. They are equal to their integer values, but that's not super important today. They're also equal to themselves, thank God. There's actually something in Python that's not equal to itself. Math.nan is not equal to nan. It's also not oh wait, it is identity. Wait. No, okay, yeah. No, that makes sense. Because of course it's identity, that's just the memory address. But yeah, this is because of IEEE floats, but don't worry about that. Okay, the cursed thing is, let's say that we have false equals equals false. What should this be? True, I agree. Thank goodness for paying attention. What about this? There's an in operator that works on lists, so there's no trickery here. What should this be? I agree, yes. Now's where the fuckery happens. What should this be? Don't think about operator precedence. First, try both of them in your head. So like, if this bit here is true, true and false should be false. Yeah. And if this bit is true, then that should still be false, right?
Yes.
Right?
Uh-huh.
Should be.
Yeah.
However, it's not. And we're going to use the AST to figure out why. This is actually a funny feature in Python. Well, yes and no. This is a feature. However, I don't think it should work this way, perhaps for obvious reasons. But the AST is actually going to give us a huge hint as to why it works this way. This is actually another one of my videos, so you're getting 2 videos in one today. If we ask the AST to parse that, we'll just use ast.dump since it's already here. False equals equals false in false. We'll actually see that this is not 2 separate comparisons. This is a single, oh, that looks like shit. Never mind, we will use AST pretty. You'll see that this is actually not 2 separate comparisons, but it is actually a single comparison with multiple operators. This is a chain comparison, which normally you see this in Python for things like, let's say x is 5. You can say, is 1 less than x less than 10? And that just sort of works in Python. This is the feature. This is the nice part of it. For whatever reason, the in operator is considered a comparison, which I guess sort of makes sense. And so, yeah, it actually evaluates this as instead being false equals equals false and false in false. And so that's why it's true.
Treat the false in the middle as the x in the...
What's that? Oh yeah, you can also do this. Yeah, that would also work. Because it's just a variable. It's actually just a constant. It's not equal to 1, it's a subclass of 1, it's a subclass of 0 if we're talking about false, but Python booleans are a little bit weird, but we don't have time for that. Okay, but anyway, this is the weirdness that I wanted to show you, that being able to introspect parts of Python can help you understand better about the lower levels here. And I use the AST all the time to try and explain weird behaviors that I don't really get, and this is one of them that I think is kind of a cool little demo. But the AST is not the reason that we've had this silly visualization up the whole time. The bytecode, that's the whole reason. That's the whole reason for the original video, and so that's what I want to talk about next. Where the Python, oh, actually, wait, no, we were going to talk about the peg parser. We kind of already did. Yes. Oh. Okay, I wanted to show you an unrelated thing. This one actually isn't related to the parser at all. Well, it sort of is, but we're going to have a little participation. Okay, so let's say we have a variable set to true. We have another variable set to true. Or we'll set the other one to false. Okay, what does not x give you? False. I agree. Cool. What about not y?
True.
Okay, good. We know how booleans work. That's great. All right, x equals equals y. False. Yes, great. Quick learners. Okay, what about this one? It's not a trick, but yeah, it's true. Okay. Here's where the trick happens. What about this one? I would think it should be true. However, it's syntax error. This is a wart that's been in the Python grammar since the first version of Python. Although in the first version of Python, there wasn't equals equals. There was only single equals. And this is due to a quirk in the parser so that it can handle this syntactically. Python has an is not operator for the opposite of identity. And so it actually parses that equals equals not, sort of like is not, and then backtracks and says, wait a minute, that equals equals isn't an is. What's going on here? That doesn't make any sense. And so that's why it's syntax error. You can, of course, put it in parentheses and fix it, but just a little quirk of the grammar. Unrelated, but I figured we're talking about parsers. We can talk about places where the parser doesn't do the right thing. Okay, let's get to the actual thing that I want to show, which is bytecode and the actual compiled part of Python. Python, again, gives a module that helps us introspect the way that it compiles down, and that is the dis module, standing for disassembler, pydoc dis. And Python's bytecode sort of looks like a little bit of an assembly code, but we're going to be able to look at it and understand it because it's actually pretty high level and pretty easy to understand. And that's the actual part of Python that's interpreted. So again, tokenized, turned into an AST, compiled down to bytecode, and then the bytecode is interpreted by a virtual machine. We're going to be the virtual machine today, though. Okay, let's go back to that first example. Just this very simple function where we assign 1 and we return x plus 1 and we print it. We can use the dis module to disassemble that entire file, although there's going to be a bunch of junk at the top, which is not so important. So it's actually, this bit up here is it building the module, and this is the function. We only care about the function, so I'm actually going to do it a different way. We're going to run this file interactively, and then we're going to import this and disassemble the function. What did I call it? Add 1. So we just see the function here, which is kind of nice. Okay, so we see the line numbers here on the left column. The middle column is the byte offset, not super useful. The opcode is what's important. This is kind of the name here. And then it may have some operands to the right-hand side. And we're going to use this visualization over here to visualize that. Okay, this will just be the basics, and then we'll show some cool / weird stuff later. So if we look at our original module, which I'm just going to do like this. Well, this is not the fastest way to do this, but okay, this is our code. We're going to start at the module scope where we have this print function, add 1, and actually we do have the, bytecode for that. So we're going to use it up here. And so this top frame is going to represent our global scope. You can kind of think about a global scope as having a name that's our function here. So print is a global function, and add 1 is also a global function. But it doesn't actually work that way, but you can kind of think about it that way. And each of these boxes are going to represent how the bytecode engine works. It is what's called a stack engine. At least I think that's the name for it, where basically every function frame has a stack that grows and shrinks and represents the intermediates in how the code is actually executing. A lot of virtual machines operate similarly. If I remember correctly, the JVM also is a stack machine. I don't know about LLVM, but that's just because I don't know. So let's walk through this bytecode and show how it executes, and hopefully use this terrible tool that I artisanally wrote some HTML for. Okay, so the first instruction that we're going to do is load name. Oh, the other cool thing about this is if you need to know any of those bytecodes, you can actually look up how they work by looking at the docs for the disassembler module. And so, for instance, we're looking at load name right now, and we can see exactly how it works. Now, granted, the documentation is aimed at people that look at bytecode all day, and so I don't expect anyone to understand what conames name I means, but don't worry about that. I've spent too much time staring at this stuff, so I can explain it. Okay, so we're going to start load name print. So our first box is going to get that print function here. I'm going to print, yes. I'm going to use sort of angle brackets to represent that it's not actually the object there. Like technically this stack is a bunch of pointers, so it's actually a pointer to the Python object that represents the print function. Cool. Next, it does push null. This one's super weird and actually something that I learned while making this demo for this particular presentation, because when I originally gave this YouTube video, this push null did not exist. This is brand new. We'll explain it a bit. So it puts a null pointer there. Then it loads name, add 1, so we get our add 1 function. Then it loads a constant 5. I really like this crappy tool that I wrote. It works really well. And then finally what it's going to do is it's going to call, and specifically call 1. this is the number of arguments that it needs to pop off of the stack. So in this case, it's going to pop off the 5. It's also going to pop off 2 more arguments. The function it's going to call and this thing. This thing that's there, from what I understand, is meant to make calls simple to implement both normal function calls and method function calls. So with a method function call, it's going to pass self in as the first argument, and so typically that null will instead be the object that it's calling it on. But in this case, it's null because it's just a free function. And so it's going to call, so we're waiting for that call to succeed, and so we're going to get a brand new stack frame here, where we're actually stepping into this add1 function here, which we have the code for down here. We've passed a parameter, so the parameter that we had was, I think it was 5, and that is our locals for this particular function. We're going to pretend like locals is a dictionary. In Python, it's not actually, but it's easy to think about it that way. And then we're going to step through the actual code of this function. All right, so first we get this resume opcode, and this one also didn't exist when I first made this content. This is sort of a plug-in point for Python. This is where like a debugger could take hold, or a profiling tool could notice, or a coverage utility, or something like that. It's sort of like a fancy no-op that you can instrument in the interpreter to do other stuff. So it does nothing. We're going to ignore it. Next, we're going to load const1. So put that constant into our single stack cell that we have there. And then we're going to store fast into 1. It says store fast. There is, I believe, no longer a store slow. This has to do with how locals are not actually a dictionary, but they're more like a struct. But OK, anyway, it's going to store the 1 opcode into our locals. So now we have a variable called 1 that's equal to 1. And that little stack cell is gone now. Next, we're going to load fast x. So we're going to load the value of x and put that onto the stack. Then we're going to load fast 1. So we load the value of 1. Finally, we're going to call binary op, which takes 2 things. In this case, it adds them together. So we're going to pop 2, add them, put 1 back. So 5 plus 1, last time I checked, is 6. And then finally, we're going to return value. So it's going to take the 1 value in this and give it back to the caller. So we can finally fill in this ... here. And this frame is gone now. And then we jump back to the actual module code here, which we were at this particular call. See, but this part's confusing to me. Oh, wait, I missed the push null here. Dang it. OK, pretend like there's another null to the left of this, because I started the code here when I should have started the code here. But anyway, there's actually a null here which represents the self for print, because again, it's a free function, so it's not going to need a self. But finally, we're going to call call1, which is going to pop all of these. It's going to print 6 to the output. Call actually returns a value. When you call print, for instance, like if you assigned the return value of print, it's none. Because, yeah, it's like void in any other language, except none is a real object in Python. And so this call is actually going to put none on the stack. None being global constant none, not the null that we saw earlier, which was a null pointer. Since that value from print is not used anywhere, we're going to pop that value immediately. OK. We've stepped through a very simple function and sort of showed how the bytecode executes in this like growing stack per stack. Because we have a stack of stack frames, and then we have a stack of the actual bytecode execution engine. How are we feeling so far about that? OK, are you ready for some weird stuff now? I'm ready for some weird stuff. So the first weird stuff that I wanted to show is a function that just doesn't do anything. And you might think, like, OK, it doesn't do anything. It shouldn't have any bytecode in it. It should just be basically empty. Well, not entirely empty, because we know it's definitely going to have this resume in it, because every function has this not resume. But it turns out this empty function actually does 3 things. One being the resume. And we can use the disassembly module to show that. Oh, okay. I'm in a version of Python where it is optimized to two things. It's actually funny, this return const has gone back and forth, I think 3 times in Python now, where if we look at Python 3.8, lowercase f. Yeah, so in Python 3.8, it doesn't have that resume thing because that's new, but it was load const and then return value. They made a super op, I believe they called it, or a super instruction, which just simplified a common operation. But it turns out when you make super instructions, it's a lot harder to make micro instructions later if you want to make a just-in-time compiler, which they're currently trying to do in Python. And so they've actually decomposed most of the super ops that they've made. So in 3.12, which I was using before, has this return const. And you might think, what is this return const? Like, why are we returning a value at all? And this was actually the first bit of intuition that when I saw this, I was like, oh, this explains why every function in Python, if it doesn't return a value, it returns none implicitly. This is actually the bytecode representation of that implicit none return. And so this was like a big aha moment when I first saw this, and like a bunch of things that I couldn't explain made a lot more sense because I suddenly had a concrete representation of why does a function return none when you don't return anything else. Let's see, what does my list of weird shit include? Okay, so we did the simple add, we did implicit return none. Oh, optimizations. So it turns out that Python, oh, you have a question? Yes.
Yeah, sort of a comment returning values.
Yeah, and we can actually show, so the comment/question for the recording was basically like, you're working on making your own toy language, and you were dealing with whether or not something implicitly returned nil, but also dealing with multiple return values. And Python has multiple return values in that the syntax sort of looks like you're returning multiple values. It actually doesn't return multiple values. And we can show that with both the AST and the bytecode. I'm going to show it the AST because I think that's the easier representation, but we can also show it the bytecode. So let's say that we have a function that's going to return, I don't know, let's say x equals 1, y equals 2, and we want to return both x and y. So we're getting 2 values out. We can also assign those 2 values later, so like a, b equals f, and so a will be equal to 1 and b will be equal to 2. I actually have a little demo that's similar to this later when I'm going to explain how swap works in Python, but you can, this is kind of a precursor to that. Although the AST is less useful in explaining that one than the bytecode. But if we AST pretty on that, no show offsets on t5.py, and we find the return statement somewhere. Yeah, find the return statement here. You can see that Python's not actually returning multiple values. What it's actually doing is packing those values into a tuple and then returning that tuple object. And so anything that looks like a multiple return value is actually just returning a tuple that contains multiple values. And the double assignment that we see later is actually just assigning to a tuple. It's not actually doing an assignment to a tuple, it's doing an unpacking, but the AST represents it as assigning to a tuple. Fun fact about that, you can actually assign to an empty tuple, because that is the trivial unpacking. This actually is useful in some cases though. So like if you have a generator, wait, does this still work? I don't know if it still works. We're gonna try it anyway. Sometimes this is useful to assert that, something never produces a value. So this would be an error if f actually yielded a value. Oh, we're off topic again. This is why I'm great at streaming and terrible at making direct content. So this should be an error, yeah. So you can see like you can actually assign to an empty tuple, which is also funny. I meant to talk about this during the AST portion, but it turns out that tuples, except for the empty tuple, the parentheses don't matter in Python. They're actually not part of the syntax at all. The actual syntax is just the comma.
Yeah. So quick question on this one.
Yeah.
It's a very interesting one.
Yeah.
And I think it's interesting that, it can be confusing. And even for someone who clearly is curious about languages, they find this aspect, is the functions returning multiple values? How does that really work systematically? And I know one of the key philosophies in the poem, the Python poem, is explicit is better than implicit. No, what was it? Is that it? Something like that. So,
Is it
yeah.
pip 11? No.
And so, what do you think of the decision to make?
I could import this, you're right.
Yeah. It's such a good poem. We should look at that. Yeah, explicit is better than implicit. The second law, when it comes to the 10 commandments, it's clearly more than 10, of Python. So I'm kind of wondering how you reconcile the fact that, some may say, if we made one way to describe tuples, so there's one way to do everything, it's also here, which is to always use the tuple parentheses. That would be explicit, and it would be one way to do a thing. So why hasn't that had a factor in the design of Python, if this is the rules of Python?
So I think the fun part about this poem is it's not very precise, and Python doesn't follow it very closely at all. In some ways, this is a pinnacle and a North Star to aim for, but not in any way, shape, or form how Python actually ended up. It's a 30-plus-year-old language. It's got a lot of baggage and a lot of compatibility to try and keep up with, and it has gained a lot of features over time that make others redundant or the same. For instance, there are 7 different ways to format strings in Python. 7. Surely we can just have one. But, oh no, we came up with a better way to do it. Now there's 8. There aren't 8. I think there's exactly 7, but not including third-party libraries. So, but yeah, in a lot of ways, like this is sort of a North Star. Some of it is like poking fun at C++ and post-increment, pre-increment. Like, there's a joke about Dutch people in here too. Poking fun at Guido, of course. Yeah, but like this is sort of things to aim towards, but in a lot of ways, Python doesn't do this very well. And no language does this well. Like all code sucks, including every piece of code. There is no good code. Yeah. But great question. Thank you for the multiple return values. There are other ways to implement multiple return values. This is just the most common one that I've seen in languages. Like some languages have their own like custom calling construct, which like says how many values are going to be moved out of the return value into particular places, and so the functions like coordinate between each other. The simplest one, at least in dynamic languages, is just to return a tuple object and unpack it later, or a list, or some sort of mapping type. Cool. Where's my little notes? Nope, that's the wrong folder. Peephole optimizer. Yes, okay. I was quickly talking about this. So Python actually is optimized, which sounds hilarious because it's not very fast, but there is a bit of optimization that goes into Python, and we can actually see some of it by looking at the bytecode execution of some examples. So let's actually make another t.py with another function. Actually, we can just do this one in the REPL. Why are they t.py? That's a great question. A friend of mine, at Yelp used to name all his temporary files T, and I was like, oh, that's short. I like that. And if he ran ls in his home directory, there was this triangle of T's of, oh, T's taken, I'm going to make TT or TTTTT. And so, yeah, I've decided to number mine instead. But. Okay, but we want to show the optimization of Python. So if we print 1 + 1, and we look at the disassembly of this particular code, we're never actually going to see 1 in there at all. We're never going to see a binary add either. There's a lot of cases where the AST analysis portion of Python allows it to peephole optimize particular things and eliminate them entirely from the resulting bytecode. It doesn't do many of these, so it doesn't make many things faster, because it turns out there's so much magic in Python that can cause plus to not do what plus does. So it can only do this in particular cases where it absolutely knows that it won't break the code. But in this case here, oops, I need to actually import this. Import this. Not import this, import this. And you'll see here that it's just directly load const 2. It's not doing 1, it's not doing a binary add, or it's not loading 1 twice, doing a binary add, and then storing it back. It's just loading that constant 2 directly. And this actually gets represented in the function object itself, and so it's not ever storing any ones anywhere in this case. And there's actually some like fun little bugs about this. I'm going to show you one really quick. Well, it's not a bug; it's just a hard to explain thing. So, small strings in Python are all the same. So. Normally, you can't ask if two things are identical because they should be two separate objects. But there's an optimization in Python that makes small strings the same. Not so small strings are also sometimes the same. Ignore the syntax warning; it kind of gives away the trick that's happening here. So, for instance, if we do a small string s is small string, you can multiply strings in Python also. So. It's really just a 2-character s string. But if we instead assign a variable and do the same thing, I is small string times I, we get false. So it should be the same, but this is the Peephole optimizer at play. So the way that this particular line actually gets compiled is as 2 small literals, and since those 2 small literals are in the same expression, they are actually the same object. And we can show that with a disassembler as well. It might optimize out this entire thing though, so we'll see. No. What do you mean syntax error? Oh, because I didn't press enter enough times and this is the old REPL. Yeah, so you can see here it did load const ss, and if we actually look at the func, where is it? Oh, code. There's only a single ss const, and so when it loads that particular constant, they're going to be the same exact object. So they'll have the same memory address. Whereas the one that doesn't do it that way, actually does that binary op in here. So it's producing a new object, and it produces that new object twice, and so you get 2 completely unrelated objects. Okay, I have 4 more things. Oh, no, we showed this one. We have 3 more things to show. Okay. How much time do we have? 15 minutes. Maybe we'll only show one of them.
More like 8 minutes, actually.
8 minutes. Okay.
Because we have to,
right.
yeah.
Funny timing.
Michigan 10.
Okay, I will
it's
show
like
you.
the other way around now.
I will show you one silly thing then, and then we can do questions. Okay, so tuples in Python are immutable. That means if you assign to them, you can't change them. So if you do this, you get an error, type error, you can't assign to them. You can put objects in tuples. So if you say x is a list, and let's put another object in there so we can see it. You have this list, right? What if you try and add to that list? This is a little bit weird. It shouldn't be allowed to modify the tuple, but the tuple is really just a reference to the list, so it should succeed. However, it doesn't succeed. I say it doesn't succeed, but it actually does. So it both fails and succeeds at the same time. And this to me was really hard to explain in any way except by looking at the bytecode. So let's take a look at the bytecode and see how this particular bit of code runs. So let's represent that same thing again. X equals empty list 2, x0 plus equals 2, and that should be enough. Yeah. Import dis.disf, and we get to use our fancy tool again. Okay, we're going to start with build list 0. Builds a list. Load const 2. Loads const 2. Build tuple. So that's going to take these 2 and convert this into a tuple. Store fast into x. So x is now this tuple. I'm trying to go fast, sorry. Load fast x. Oh, I should have just left it. Damn it. Load const 0. This is where shit gets weird. Copy 2 I believe that copies, I forget how this one works. I'm pretty sure it copies the, all right, we're gonna ignore most of that. We're gonna get to this part. This does a bunch of like weird stack flipping so that it doesn't have to duplicate these two things twice. But let's actually get to where we are here, which is where we should have, we're gonna ignore some other stuff here. We should have that list object that we have, and we should have built another list here, build list, or load const 2 build list, so we should have a list containing 2. And then we're gonna call binary op plus equals. And so at the point where this binary op executes, we have just this list object and this other list object, and list supports in-place add, and so it takes this and in-place adds it, which modifies all of the references to that list. Then it's going to try and store subscur. It's going to try and store into the index in that tuple. And so the opcode at 34 is where it actually fails, but it's already performed the side effect at opcode 26. And so that's why this weirdness happens. And to give you more time for questions, I skipped a bunch of this stuff there. But copy does some funny stuff with moving opcodes around in the stack and reduplicating them. So it just saves some code. And now we have time for questions. You can ask me literally anything. Career advice, why I'm showing you weird shit about Python, or anything. Open source. Yeah. You.
So if you were, so as far as I know, tuples are hashable. Does this mess with that because you change the value of the tuple?
Yes, so tuples are hashable if all the things that they contain are hashable. So in this case, like a hash of a tuple containing a list is not hashable because the things inside of it are not.
That makes sense.
But yeah, if it contained only immutable things, then you can get hash.
I've seen like with data classes, if you enable hashes, it's like unsafe underscore hash.
Yep.
So you can still modify it.
Yeah. Data classes are a little bit funky, and one of the reasons that I prefer name tuples over data classes is name tuples are actually tuples, and so they give you that true immutability. Whereas you can actually, like you said, unsafe hash, you can muck with the values and break the hash in a weird way. Yes.
Compared to like an explicit language like C++, where I think like the instructions are more clear to what they're mapped to in assembly.
If you ignore undefined behavior.
I guess like relative compared to Python, which has a lot of this like under the hood AST things.
Mm-hmm.
I guess I'm just curious like what your thoughts are in terms of like language design, picking the right language, because there are two very different approaches to programming.
Yeah. Okay. So the question was like, compared to a relatively explicit language like C++, where things are supposed to work in one way, how would you compare Python? And I would actually question that first statement a little bit, in that C++ is just a language specification. In the same way that Python is just a language specification. I'm showing you the implementation details of CPython, but even C++, there are different compilers that go through similar phases like this. There are different output targets. Like you can write a compiler that directly targets, the instructions for a particular processor, or you could write one that targets LLVM, and instead has a different execution engine that has its own like tiny bytecode machine. Like, there's nothing about the language itself that dictates how it should result in machine code, except for like a few parts of the spec that are. We won't talk about those, but I would actually say that C++, like in a lot of ways, doesn't dictate what the outcome of the actual binary is. It tells you more about like the abstract machine of the language. Yeah.
Did Python start off with a stack-based bytecode?
That's a good question. I actually have if you want to find the answer, you can actually build Python 0.9.1 from source. Because I made it compile on modern computers, if you really want to. I'm pretty sure the answer is yes, but
according to ChatGPT, it's yes. Python 0.9 in 1991.
So in many ways, the misinformation machine is usually wrong, but it looks like it's actually correct here because it's the same. This is the same disassembler module that we were talking about before in Python 0.9.1, which was released before I was born, barely.
And unfortunately, the university recording cut off. There was one question at the end that was asked that I actually think is really good, so I'm going to reiterate it here. The question was basically like, I'm often thinking about trying to make something, for myself, and I have this like nagging voice in the back of my head that's always like, someone else has already done this, or someone else has done this better. I shouldn't bother because someone else is built something already in this space. How do you reconcile with that? And my answer to that was, ignore that screaming voice in your head. Just fucking build it. Like, you will learn a lot building something. You'll often build something that's more specific to yourself. You'll hopefully enjoy building it and use it. And this was in context to like, why did you build a text editor? Obviously, there are better ones out there already. And like, I think, in retrospect, I wouldn't go back and build another text editor, but I'm really glad that I did, because I learned a lot in building it, and I definitely had to block out some of those thoughts of why bother building this in the first place.